Welcome back, everybody. I realize many of you found that last test pretty brutal, and even the ones that did well weren't confident that they did well before they got their grades. It's that last section had a lot of application stuff in it, and it tends to be harder. The students that did the homework, for the most part, did well, and students that did some of the homework but didn't do all the homework, and they sent in some sections, I could tell which sections they did the homework on based on their exam, because they did well on those problems but not well on the problems they hadn't done the homework on. It's really worth your time to do the homework. Even though it's not worth points, it's worth knowledge. And it's the only way you're going to pass this class is with knowledge. You can always take an instructor that will hold your hand and give you points for homework. But the result of that can be you passing a class with a C that you failed all the tests. If you get 20% for homework and do all your homework, and everything else is on tests, you can get 50% on all of your tests and still end with 70% and pass the class. But since you did poorly on all the tests, you don't understand the material. Homework is for point-wise, it's a crutch. Please do the homework for your own good. You'll find that when you transfer or go to graduate school, they don't give you points for homework. Having said that, the show must go on. Hopefully, I will have the test back. Hopefully by Thursday. I'm waiting for 2 students to have submitted it. They're doing it in the AAC Center. And I'm waiting for those results before I hand it back. I will type these up and put them in Canvas. I just threw them up because I realized I hadn't put anything up already. And I will have them up later. I'm guessing many of you took a picture. I will scan this into the lecture notes as well. We have something like this on in the file section, like a cheat sheet of formulas. This has got all the differentiation, popular differentiation integration here. It might be worth taking a pic of it just to reference while you're doing your homework until you've mastered it. I strongly recommend doing flashcards for each direction on these. You already done all the left stuff, the derivatives, but the stuff on the right may not be as intuitive. So I'll leave it up. I'll zoom it in a little bit so picture comes in a little bit better. Once it focuses. It's almost too bright. Throw that back in. And we had talked about doing the integrals. We have looked at how it's set up, but we haven't actually done any yet. So let's start taking a look at some integrals here. So this is continuation of 5.2. I'm sure we're going to get through 5.3, and we might get started on 5.4 today. So 5.2 continued. And this is the indefinite integral. And as a reminder, the way it's set up, if capital F prime of x equals little f of x, then the integral of f of x with respect to x is f of x plus some constant of integration. So its derivative is going backwards. So we can start off with a simple one here. Let's integrate 8x cubed dx. Go ahead and give that a try. See what you come up with. What do you need to take the derivative of to get 8x cubed? Or you can do it the way we talked about previously, polynomials. You go up a power and divide by the power. Remember, when you have your result, you can always take the derivative and double check that you get back to the 8x cubed. Give you another 20 seconds. All right, so I've got a cube. If I took the derivative, I had to start with 1 degree higher. I should have an x to the fourth. And when I take the derivative of something with the fourth, I multiply by 4. We're going to undo the dividing by that. So by dividing. So we go up the power, and then we divide by the power. And I get 2x to the fourth plus some constant of integration. The c is important. You may not think so because you haven't done definite integrals yet. The c lets us know we have not given it any region that we're doing this integration over. Because remember, we started this chapter with doing area under the curve. And we haven't set what area we're doing under the curve. So the c tells us we could be doing different regions. Like 8x cubed. Well, x cubed looks, 8x cubed is pretty steep, but I'm going to make it less steep just to show the picture. Without those, like the area defined, we could be talking about like this region over here. I could be talking about from here to here. Like, I don't know which region I'm looking at. So the C lets us know, the C tells us there's a family of solutions that has this. And depending on what conditions we have, this might have actually gone up some. Like a constant would have elevated this. I'll get back to that. Let's take a look at some more. What about 5? I need to make it look more like an integral and less like an S. 5 sine x dx. So a helpful way to go with this is go say the derivative of what equals sine x. Well, the derivative of cosine x gives us what? Negative sine x, yeah. So it's not quite cosine x. If I multiply this by a negative on both sides, I will get what I want. And so ddx of negative cosine x will get us sine x. So sine x becomes cosine x. There's a negative, and the 5 is still multiplied by it. And we have some constant of integration. Oh, that got blurry on Zoom. Ready for another? So hopefully, well, eventually you can, or hopefully you will skip this step pretty soon, but we can break this up into 3 integrals. That step is optional. It's more of a teaching tool than anything else, because then we apply it to each one. Here we go up a power and divide by the power. And I'll call that like C1. And then up a power and divide by the power here. This is a minus C2. And up a power here, this was x to the 0, so up a power is just x plus C3. And again, that step's skippable. We don't know what any of those constants are, so I could just lump them all together as one big constant, where C here equals C1 minus C2 plus C3 from the previous line. But this is the end solution, the end result. If you don't do this, don't do it. This illustrates what's happening for those that aren't following the integral thing. You can slow it down, do integrate one thing at a time. Hopefully by the end of this class, if not the next, or the end of this semester, if not a little bit into Calc 2, you're comfortable going straight from the blue line to the red box here. Because you're just going up and dividing by it. Polynomials are the easy ones. Sometimes they get more challenging. For example, I guess I could put lines between these problems. The integral of sine x over cosine squared x dx. Any ideas on what we could do here? Because we don't have a technique for that, do we? Yet. We'll get a technique for this, but we don't have one yet. But there is something we can do in the meanwhile to get what we want. Any ideas?
Make a tangent.
Make a tangent. I like that. Let's try that. So like maybe separate this out into like 1 times sine x over cosine x times cosine x. And that way we get like a tangent x over a cosine x. You still have our integral dx. It may not look like we've made progress, but we are. What else could we do? If you're not sure where to go from here, think about the derivatives. We're working with trig functions. Think about the derivative of trig functions that we know. What are the results, and can we produce one of them here? For those of you that don't remember your derivatives of trig functions, we're right there in the middle. Can we produce any one of those in this integral here?
Secant.
It looks like secant. We already got the tangent, right? Do we have the secant? 1 over cosine is secant, right? So I could write this as secant x tangent x dx. And we just saw that we looked at the table of derivatives, that is secant x plus some constant of integration. So if you're not sure what to do, experiment. Yeah.
Integration is just taking the antiderivative.
Yep.
Oh.
It's doing derivatives backwards. Right now we're doing it without, it effectively finds the area underneath the curve f of x, little f of x, the one inside the integral. When we have edges, when we have like a start, like an A and a B, right, when we're doing the rectangle thing, when we have those, it'll actually find that area. We will get there. It's very similar to those are called definite integrals. And those don't have constants of integration because it's set. You already know what it is. The indefinite integrals have these constants of integration because we don't know what area we're looking at, what region. But yes, it is working backwards.
What section is this?
This is still 5.2.
Oh, okay.
You guys ready for another one? I love playing trick the student. Trick the student is fun. I try not to do it on tests. When I do trick the student on a test, it's usually I done thought the problem was gonna be easy and it wasn't. You were not tricked on this last test. Everything was designed as intended. How can I do this one? Oh,
Like bring the X to the board to the top, make it hidden.
let's try that. Let's see what happens. If I bring it up to the top, I've got this. Now what? It's the right idea. You're going the right way.
You multiply it out.
Distribute it through. What happens when we x squared times x to the -4? What do? You add them. So 2 plus -4 is -2. And that one's already there. Now we can do the integral. This is where haste is gonna fuck you up. Because it's really easy to start trying to do derivatives and you do the numbers the wrong direction. You get so used to doing an entire semester of derivatives that when you start doing integrals, you start doing the wrong shit. We need to go up a number. The power's got to go up. Up from -2 is what? -1. It's not -3. So then we're going to divide by that -1. If we go up from -4, we get -3, and we'll divide by -3. And then we have a plus c. This ends up being, if I get rid of the negative exponents, -5 over x plus 8 over 3x cubed plus c. Does that make sense? Did I skip something for anybody? Alrighty. Oh, here's the fastball. One of the Friday night labs in the Mesa Center, from 6 to 9 coming up pretty soon is the integration bee. What day is it at? You get to watch, if you go to it, you can see all the calculus 3 students, calculus 2 students competing for cash prizes. That's teachers throwing money. I think like the winners were taking home $50 last semester. Let's see. FNL. December 1st. Oh, it's the derivative b, not the integration b. Derivative b. I wonder how the Sign Club is doing it at FNL. It's on December 1st. If you're interested in competing for prizes, I think you guys could, some of you are up to par, or quick with the derivatives. What's the answer here? Matthew.
On the constant, would it add an x? adding a, up on a power, like a 3 would be 3x.
Yes,
Oh, okay. I got 7x to the third power divided by minus 3x squared over 2 plus 3x plus 8.
close, but that's what we got last time.
Oh.
We actually, you might have been walking in when we did it. We actually did this problem with, got that. I've changed something. Something's different here. Madeline, it's e of t, so the variable we are integrating with respect to is t. Ah, sneaky. I've took down some of the smartest students at the campus with this shit on the integration bee last semester. This is constant with respect to t. That would be taking the derivative.
Yeah.
So the integral would be 7x squared minus 3x plus 3t plus c. And if you wanted, you could distribute the t. Don't worry, I won't do that on a test. But I did want to make sure that you look at the constant or the variable that's being integrated with. This actually becomes really important when you hit calculus 3 and we start integrating in 3 dimensions. Right now, we're just integrating in 1 dimension. This is child's play. Calc 3 is the good stuff. You guys ready for the next one? This next one's a bitch. Promise you. It's too bright. The fuck happened to the brightness when I looked up? Oh, this Friday, Friday Night Lab has someone from Microsoft there talking about how to get a job in that type of field. Get internships, jobs, and stuff like that. What kind of things you should study for working in places like Microsoft or other, the equivalent Yahoo, Google, shit like that, the tech world. So it's someone that works at Microsoft coming to give a guest presentation on Friday night. If you're interested in that as a future job, it's definitely worth showing up for. I will be there because I don't want to teach you minions forever. No, I'm teasing. I love my teaching job. I don't want to work for Microsoft. This is tricky. Any ideas? You're probably, if I gave you an hour, you're not going to come up with this. I can write this as x squared over 1 plus x squared. And I am going to add 1 to it on top, and I'm going to subtract 1 from it. This is sneaky bullshit. This is some sneaky bullshit. This is worse than DT. Because now I can break that up into 2 integrals. 1 plus x squared over 1 plus x squared dx minus 1 over 1 plus x squared dx. What's the first integral? Let me throw an intermediate step in there and simplify it for you first.
X plus C.
X plus C. I'll call it C1 because it's not going to be our final C. This one may not be one you remember, but it is tangent inverse. So we will have X minus tangent inverse X plus C. So again, this generates a family of solutions. They call it the general solution. Another name for this is the general solution. You guys ready for more? The next problem gives you a very small, easy sample of what the last math class that we teach at COS is. Differential equations. Does anyone still need this page up? I can't tell if anyone's still writing or not. All right. So this is something called a differential equation. Find f such that f prime of x equals x squared plus e to the x, and f of 0 equals 4. So if we want to find f from f prime, we needed the antiderivative. So we will be integrating the f prime of x. X squared plus e to the x dx. What is the integral of that? I don't know.
1/3 x cubed plus c dx plus c.
Bingo. So this is the general solution. And that's f of x. We integrated it, we found f of x. That's the general solution. But we were given one more piece of information. We were given that f of 0 equals 4. So if we do f of 0, I'm going to plug in 0 everywhere I see an x. And that should equal 4. So that's 0. E to the 0 is what?
1.
1. So it looks like I can actually solve for c here. And if I replace C in the initial equation into the general solution, this is called a particular solution. And f of 0 equals 4 has a name. This is called the initial condition. Frequently, the initial condition is at 0. Often, initial condition is at 0, but it doesn't have to be. In fact, it's why we call it as initial condition. It's where it starts at. If we were doing, say, this was with respect to time, when time starts t equals 0, it would be like right out. Generally, t equals 0 is the current moment. We're in where we start the experiment. That's just a little sample on let's stop. Let me see if I can come up with a harder ones for you. There we go. Problem sets. This is the good stuff. Oh, stop being numbered. Here we go. 5.2. Load already. Oh, let's try this differential equation thing kicked up a notch. F double prime of x equals -4 sine of 2x. F of 0 equals 1 and f prime of 0 equals 5. Find f of x. Ooh, supersize. Hey V, are we having fun yet? So what kind of approach could we take? If I need to get f of x and I've got f double prime of x, it sounds like I need to integrate twice. That way I get rid of the second derivative. If I integrate f double prime of x, I should get f prime of x plus some constant. And I'll call it C1, why not? And we can find out what that constant is using this initial condition. And then when we integrate f prime of x plus whatever that C1 is, I need a dx in there. Quit being sloppy. I should get f of x plus C1 is probably going to be a number, so C1x plus C2, and then we could use that. But all of this will be f of x. That is the final form of f of x. So give that a gander. The lights hate you. Let's see how you guys are doing. Anyone finished? All right, let me give you a little bit longer. think that 2x is really throwing you guys off, isn't it?
Yeah.
Why not, let's switch to, if you haven't gone very far with it, just do x. Let's see how you do with x.
Since,
-4,
yeah, it's fine.
you can just move it outside the integral. So this could become -4 integral, single integral of sine of x dx. Actually, let's do 2x. What do I need to take the derivative of to get sine of 2x? Well, I know the derivative of cosine gets me to sine. So if I did the cosine of 2x, what would I get as the derivative there?
Negative sign.
Close. -2 sine 2x. So if I wanted sine of 2x, what I can do is divide both sides by -2. And the derivative of -1/2 cosine 2x is sine x, sine 2x. Chain rule.
Oh,
It'll get you every time. So the chain rule allows us to, we're gonna, in 5.3, there's gonna be an easier way to do this chain rule in reverse, because what we just did is the chain rule in reverse. There's an easier way to, like, not an easier way, there's an organized way of doing this, rather than writing out what we did here. But if we integrate that, we get -1/2 cosine 2x plus c. I could put the -4 on the c, but that's just, it's still going to be a constant of some form. This is f prime of x. So if we do f prime of 0, let's clean that up a little bit. I have 2 cosine 2x plus c. Now if I do f prime of 0, 2 cosine 2 times 0 plus c, I should get 5 based on that initial condition up top. So what's cosine of 0?
1.
1. So I've got f prime of 0 equals 2 times 1 plus c equals 5. I don't need that part anymore. C plus 2 equals 5. If I subtract 2 from both sides, I get c equals 3. So f prime of x is 2 cosine 2x plus 3. We're getting there. Well, we want to do this again. And I'll rewrite the initial condition that's important for this line. Since it's off screen now. So we got to do that thing again. ddx of what gets us cosine 2x? Well, sine of 2x would get us there. But what's the derivative of sine of 2x? Anybody? Madeline? It's 2 cosine 2x. That chain rule kicks in. So if I want cosine 2x, I could just divide both sides by 2. I've got 1/2 sine 2x. Derivative of that. Let me rewrite that where it's a little less sloppy. So if we integrate cosine of 2x, this 2 is right there. The cosine 2x becomes 1/2 sine 2x. And the 3 becomes just 3x. Then we got another constant of integration. This is our f of x. Yeah, go. We could have done that. We could have noticed. I was going to point that out right now. We had the 2 cosine 2x. I could have just used that and ended up with sine 2x. The way I did it, that's not always going to happen that way. So it's good to get in the practice of doing that dividing thing. You'll see that when we distribute that 2 and that 1/2, we still get sine of 2x. And right when we finish this break, we'll take finish this, we'll take like a 5-minute break. We'll start 5.3. Now we're going to evaluate our initial condition, plug in 0 everywhere we see x. And that should equal 1 based on our initial condition right here. What did we get for C?
1.
1. That's 0. That's 0. So 1 equals C. And we replace that back into f of x. We get our final form. Bam. You just did differential equations. Good job, folks. All right, let's take like a 5-minute break, then we'll come back to 5.3. 5.3, we're going to look at what's an easier way of addressing this situation right here. Pause the video. All right, so 5.3 is on integration by substitution. And we call this the U-sub. I'll use a capital B because my little b's look like 6s. I'm going to go back and look at that cosine of 2x real quick. I know there was more in it, but how the general, like the quick, like the obvious method of how this works, not obvious, but rather than giving you the F's and the G's and all that good stuff, that's the actual, let's teach it this way. The idea is if we have a chain rule going on in the original derivative, make something equal U. So I'm going to say U equals 2x. And then I'll take the derivative of both sides, du equals 2 dx. Well, it's kind of like taking the derivative of both sides. The real derivative of both sides would be du dx equals 2. But du and dx are called differentials. We looked at them before. We can do that.
What's the difference again?
Not a lot in terms of what we're doing right now. It's a lot of semantics between differentials and what's going on here. Du equals 2 dx. We don't have 2 dx here. We just have dx, so we'll divide by 2. 1/2 du equals dx. Now we're going to replace everything in the integral with the u version. 2x becomes u, and dx becomes 1/2 du. And we can put that 1/2 out front. We can move it all the way outside if we'd like. These constants can move inside and out of the integrals. And now what's the antiderivative of cosine?
Opposite side.
It's the opposite of sine. Look at Miss Rodriguez just coming in and putting you guys to shame.
Math one.
Come on, you guys gotta beat the chem teacher in this game. Come on, guys.
Let's play game.
Negative sign. I'm gonna put the negative out front. This is negative 1/2 sine of u plus a constant. But we didn't start with u. It doesn't end with u. That sounds like a threat, right? You just listen to the words I said. This didn't start with you, it ends with you. Doesn't end with you. U was 2x. So what we do is whatever's giving you trouble, maybe substituting in a u will help. Substituting a u will help. Just remember to get rid of it at the end. To replace u at the end. Right, let the chem teacher whoop your ass. Malin.
I thought the antiderivative of cosine.
You're right, it is. I let Miss Rodriguez throw me off track. I'm totally listening to her. She got it wrong, and I'm like, yeah. In my face.
Sorry, David. I just tried to remember. I love that.
Excellent work, Madeline.
Love it.
Good catch. The derivative of sine is cosine. How could we have checked that Miss Rodriguez was wrong?
It's opposite, right? The integral of cosine is sine, the integral of sine is opposite cosine.
Yeah.
Which one is the opposite?
So we could have checked if Miss Rodriguez was wrong by taking the derivative of this
Sorry, dude.
and seeing what we get. And we would have gotten negative 1/2 cosine 2x times the derivative of the inside, and that would have given us negative cosine 2x. So we could have seen she was off by a sign.
Sorry, dude. I love that.
It's okay.
I love it.
That gave the students a chance to prove that they know,
So,
prove themselves. The students have redeemed themselves. So the general form and the way it looks here in terms of the way they teach it, where it looks like the chain rule. Let's do that version real quick. They go, if we have the integral where it looks like there's some function inside another function, and then the derivative of that function on the outside. Hold on, let's start the other way. Let's see, how do we get this result? How do we find the answer here? Let's start the other direction. Let's start with f of g of x, and we're going to take d dx of this. We're going to take the spatial derivative of this. By the chain rule, you take the derivative, like I've got f as the outer box, g of x as an inner box, and chain rule just keeps going inside. So this would be f prime, and we leave the g of x alone. And then we go inside the little box, and we got g prime of x. That's the chain rule for us. So this goes the other direction. We should end up with, when we integrate, we should get back f of g of x plus some constant of integration. We're going to do that by using a u. If u equals g of x, then du equals g prime of x dx. So this is my u, and that's my du. And we have f prime of u du. We integrate that, we get f of u plus c. And we didn't start with u, we don't end with u.
Divide by
I'm not dividing. Sorry, that does look like division. Maybe let me make this, I'm saying this is u and this is du. Sorry, I was trying to indicate it. Thank you for pointing out that. That's the big form of it. You guys ready? See a couple pins still gone. I don't want to rush you. Some of you, back to thinking about the tests that I just graded, some of you guys, I think, are getting in your own heads. I know you guys know the basic derivatives and stuff, but you'll get stressed out. I recommend taking a bunch of deep breaths whenever you need to during the test and holding your breath. Like do like 5 deep breaths in a row, hold it until you can't hold anymore, let it out. Release the tension, the stress of taking a test. And you might do better. I think you'll get out of your own way. Because I saw some of you do like the word problem, Some people got the word problem right, even the extra credit right, and then missed like some other stuff that was much easier. So it's like, you know how to do it. You did the hard problem. All right, let's look at some examples with integration by substitution. Let's see. Let's start off with a simple one. I deliberately made this so you do not want to multiply it out. If I had said 4x plus 3 squared, some of you would want to multiply this out. But who wants to use binomial expansion to the 8th power? So if it was just x to the 8th, it'd be easier to integrate, right? Like, what would the integral of x to the 8th be?
X to the power 9 divided by 9.
X to the power of 9 divided by 9. Thank you, Matthew. So if we can get something looking like that in that form, we're going to be good to go. With that in mind, let's make that a u, where we'll have u to the 8 and 8th power, and we know how to do that. We just did it over here, but with x's. So u equals 4x plus 3. So du equals, well, what's the derivative of 4x plus 3? What? 4. And then a dx. So dx equals 1/4 du. And we'll replace that with 1/4 du. So I can move the 1/4 outside. And as Matthew pointed out, the integral or antiderivative of u to the 8th power is 1/9. U to the 9th. Plus some constant of integration. Don't leave it as 1/4 times 1/9. That's 1/36. And don't leave it as u. We had u right there. We're going to replace this with 4x plus 3, now to the 9th power plus c. Now, presumably, if we had done the expansion on this and got it as some giant polynomial, 4 to the 8th power, x to the 8th power, plus a bunch of other stuff, and we integrated that, and we were able to factor it, we would get this. This was much quicker. The same would have happened if it was something simple like a square. You guys ready for another? Some pins are still moving. Let's finish that up.
I miss this, dude. So much fun.
Calculus?
Thanks, you come to your class. Second.
Oh yeah. I'm not doing it spring, but next fall, I think I'm gonna. Matt said he doesn't care if I take a class. Do it again. I'm enjoying it. I normally teach evenings, but I really enjoy doing the calculus classes. And if I don't get calculus 3, which I don't know that I will, Benita is like a sniper with that shit. There's 2 of them, and if I don't pick it first round, she knows them both. She's got like first round draft pick. So I literally have to make calculus 3 my first pick. I don't know that I want to do that. So I think I'm doing calculus again next semester, not spring, but fall. And you can come and enjoy the whole fun. It's probably be better next semester because this is my first semester teaching it, so I'm working it off kinks right now. At your guys' expense. Thank you. I appreciate that. Let's upgrade this. Let's make it a little harder. We're going to do 2x plus 1 times the square root of x squared plus x plus 1. And then we're going to have dx. We have any ideas here? No.
It is.
I did what?
Don't know how to say.
We want to get, do we want to get rid of the 2x plus 1, right? Would this make this easier? She might have it in boards you're looking for.
Like use the, what's in the square as the U sub, it'll cancel, it'll divide out.
Let's take a look. Let's see if Madeleine's right. If we say the U equals, it's always worth checking. Whether you're wrong or you're right, try it. Sometime when you're doing the homework on this shit, sometimes you're going to be wrong. In this case, I don't think that she is. What's the derivative of x squared plus x plus 1? 2x plus 1. Then we have a dx. And rather than, we could divide by it. I don't like dividing by it. Let's just leave it as it is. This is my u. These two pieces together are my du. So the square root will turn into the square root of u. And the 2x plus 1 times the dx turns into du. That does make it simpler, but how does that help us? Where do we go from here, Madeline?
You just.
How do I do that?
Well,
That's the next step. Convert it to fractional exponents. Exposition, what the hell? Just spitting out words that got exp in them. We integrate that. If you go up the power, up to 3/2, we could divide by 3/2, but that's a pain in the butt. You're better off multiplying by the reciprocal. Plus c. If you divide by 3/2, you can see that you'll eventually get there. You have to clean it up. Multiply top and bottom by 2/3. The bottom goes to 1 and the top goes to that. But we've got 2/3 times u to the 3/2 plus c. And we didn't start with u to the 3/2. We didn't start with u. We're not going to end with u. We had x squared plus x plus 1. That is our integral, our antiderivative. Are you in Chem 20 in fall, from 10 o'clock to 12?
And, right now, I
Oh.
have Chem 1
Chem 1, what's going on in fall from 10 to 12?
on Tuesday, Thursday,
Yeah,
Chem 1. So we try to put Chem 1 right after Calc 1,
okay, so that's how it should be in fall.
so they can go.
You know what? We're picking our classes soon. I'll pick this class and then I'll sit in on your class. How's that sound?
Yeah.
And then if you feel like it, you can come and sit on my class and we'll go up to your class together. Up to you,
You can plan.
right? Exactly, that's what I was thinking. Matthew, you look like you had a question.
It's what's substitution?
We substituted DU in. What's the question?
Like du is equivalent to 2x plus 1, so why didn't you just? Is it not there anymore? Am I missing it?
The 2x plus 1 got eaten up. Let me show this the other way. Go back a hair. And we had that for our u. And du was 2x plus 1 dx. If I solve for dx, I divide both sides by 2x plus 1. I get dx equals du over 2x plus 1. And so if I make that substitution that way, I have my original integral of 2x plus 1. I have substituted the inside with u. And dx gets replaced with du over 2x plus 1. That's another way of looking at it. And if we do that, you'll see the 2x plus 1's cancel. And we get that square root of u du. So that's kind of what happened to it. Does that make sense?
Yeah, so the future, is that like a general substitution for dx? And it's like it's like a polynomial,
Uh-huh.
will it cancel most of the time?
As long as it's multiplied like that, yes. That's the idea of doing the U-substitution in the first place. It's to make the problem solvable. It's only when we have like a couple things multiplied together. And it may not be obvious that they're multiplied together. Sometimes you don't even need anything multiplied together, like in our next example. Our next example, we're going to integrate secant squared of 5x plus 1 dx. Are we doing? Gotta be. Yeah, we set up the classes together. I was there. We were both sitting next to each other when we set up classes for fall. That seems like so long ago. I hate planning a year in the future. I really do. I barely know what I'm eating for lunch or dinner tonight. Lunch today. Planning a year ahead. That's like getting married every year. Having to plan ahead like that. We've got some friends getting married in January of 2025, and they just let us know. And we all play board games together. And everyone else, I said, "Oh, I'm sorry, we're all playing board games that day. You're going to have to change your wedding gift." I cracked myself up. They're like, no, we'll play board games still. We're just going to get married first. What could I substitute here? Well, where's the problem here? Secant feels like a problem already, doesn't it? If this was secant squared x, do we have something that's the antiderivative of that? What? Tangent. Look at Madeline's on fire today. She's just dropping bombs in here. So let's make this look like secant squared. But without that nasty 5x plus 1 in there. Let's put in a u. To do that, we're gonna have to say u equals 5x plus 1. So du equals 5 dx. I totally want to refresh my Chem 1 because I really want to like sit in on Chem 2 because I remember Chem 1 being not only easy but fun. And I remember hearing everybody complain how hard OChem is. I'm like, how much harder can it be? You all probably thought Chem 1 was hard too. So there's a bunch of people being crybabies. I really want to like see if OChem is as hard as everyone says it is. And the only way I'm going to do it to give that a fair shake is if I redo Chem 1. All right, so I don't have a 5 dx here. So I'm going to divide by 5 or multiply by the reciprocal, 1/5. And that's going to be my dx, 1/5 du. You can either have the 1/5 on the outside or on the inside. I keep putting it on the outside. I'm going to leave it on the inside just to make it clear that it's okay to be in there. And as Madeline said, this was tangent. And we didn't start there. We're not going to end there. I was just looking at the next problem going, this is going to be fun. Oh, this next one's a doozy. It's a doozy, I tell you. Can I make someone cry? I think I can make someone cry right now. Let's put that next problem on. Oh, some pins are still gone. Don't get hasty. You guys ready? All right. Oh, this is good. What are we gonna do? We do here. What's causing the biggest problem right now? Because I know some of you are going, looking at going, the derivative of 3x or x cubed is 3x squared. I can get an x squared from the x cubed. But the problem isn't the x cubed, is it? The problem is having something weird to the 3/2 power. Right? So let's take a look at doing that. What if we made u equal 1 plus x squared? du is what? Two x. All right, so I'm gonna write dx, I'm gonna divide both sides by 2x. And we're gonna make the substitutions that we have. X cubed is x times x squared, so we can generate an x there. This is gonna be the 1 plus x squared gets replaced with a u. And then I have x cubed, which I'm gonna write as x times x squared. And dx gets us our du over 2x. So I have u to the 3/2. One of the x's cancels and I get a 1/2. But I still have an x squared du. So we have an issue here. We have a problem. We still have x's in there. What can I do about that? Because I can't integrate it right now, because x is a function of u and u is a function of x. I can't just integrate with u right now and leave x alone, because we have x and u is in terms of each other. So solve this for x squared by subtracting by 1. Well, I don't know. Let's see. Let's give it a try. It's always worth a try. Let's plug it in. Does that make this doable? Can I solve this now? I can't. Not as is though. What do I got to do first? Nope. Distribute. Don't overthink it, Matthew. Don't overthink it. Distribute if you can. I saw this on the test. I saw something like this where you had to take the derivative on the test. Like you ended up getting something like this in one of the steps as a derivative, and you need to take the derivative. And it had ugly powers in it and stuff like this. And they didn't distribute and they messed up the product rule because it's a pain in the ass. But if you just distribute here, everything gets easier. 1/2, this is u to the first power. So we add exponents. 3/2 plus 1 is 3/2 plus 2/2 is 5/2. Minus, I'll leave the 1/2 out front, u to the 3/2. What?
This is fun.
I thought so too, but it's figuring out what to do. And sometimes just like not trying to get the whole picture at once, just doing a baby step and seeing what I have left and seeing what I can deal with is the way to go. So we integrate this, what do I get here? If I integrate u to the 5/2, what do I get? Well, what's up a power here? Dalton.
2, 7, 6, u to the 7.
Yep. So we up a power and then we multiply by the reciprocal, the 2/7. And then this one is hopefully you guys saw that pattern. U to the 5/2. Plus we have a C. So if we clean this up, we have 1/7 u to the 7/2 minus 1/5 u to the 5/2 plus C. But we didn't start with you, so it doesn't end with you. It ain't about you. That's a better way. That's a better joke right there. It isn't about you. I feel so like terrible. Why am I writing 1 + x squared? I know better. I should probably write it with the x squared first. That's starting to make me twitch. We do stuff in decreasing order. That's it. Don't try to clean that up. There's no clean that up. Because there's a square root there times cubics and squares. You guys ready? Okay. We just did this problem in the 5.2 section by switching to secant and tangent. I didn't have theta, I had x. But now we're going to do this the U-sub method. Last time we switched this to secant theta, tangent theta, and we integrated and we got secant. Well, now here, when you've got sine and cosine like this, shoot for the denominator. U equals, it's worth trying the whole denominator. Try the whole denominator. If I do du here, I get, because remember, this is cosine theta squared. So doing the chain rule, we get 2 cosine theta negative sine theta d theta. So I have a sine theta d theta in the initial problem, but the cosine squared theta eats up all my cosines, and they would be on the bottom anyways. So this didn't work. It's always worth trying the whole denominator first, though. So instead of doing the whole denominator, maybe just try part of it. Let's do u equals cosine theta. Because if I substitute this in, let's look, I guess I should have pointed that out. If I solve for d theta there, I got d theta equals du over 2 cosine theta. I guess it could work. Let's see what happens here. There's a negative and sine u, not sine theta. I think it's easier doing the other way, but let's check this out. So I have the cosine, or cosine squared, is that the 1 over u. And then I have sine theta times 1 over negative 2 cosine theta sine theta du. The sines will cancel out, but I still have a cosine theta there on bottom. Actually, I guess we can make it work. But we're going to do it both ways, though. How can I get rid of the cosine theta? Well, I don't want thetas at all. We're working in U's. So let's go back to how we define U and theta together. So the square root of U would equal the square root of cosine theta, or square root of cosine squared theta. That would get me cosine theta equals square root of U. It actually gets us a plus or minus square root of U. This is gonna be tricky. But we could put that in. And U to the one, it would be U to the 1/2. So if I rewrite this, I could rewrite this as U to the -3 has du. And I'm still a little iffy. What's going on? What's going on here? I'm not gonna feel good if I need to use a plus or a minus there. But let's pretend it's the positive version and see what happens. If I integrate this, what do I get? What's up a power on this one? -1/2, right? Then times -2/1 plus a constant. So we're gonna get U to the -1/2 plus C. And U was cosine squared theta, or cosine theta squared to the -1/2. And we get 1 over cosine theta. Because this will be cosine theta to the -1. Which puts it on bottom. And that will give us secant theta plus C. So actually it worked. It does work. I want to show you the U equals cosine theta the other way before we go. I want to give everyone a chance to do this though, because I'm not real happy with the plus or minus. We happen to know this is the right answer because we already did this problem an hour and a half ago, a different method. But that plus or minus is really, it's making my eyeball twitch. I'm not feeling good about it. I feel like I did some hand wavy shit right there. So let's change it up and let's try doing U equals cosine theta. I don't like doing hand wavy stuff. And we're gonna give U equals cosine theta at Gander. Rude, power by. I accidentally hit the button. Thanks, Julie.
Okay.
Come on, power on. And now when I replace this, I can feel pretty good about it. This is 1 over U squared. And I have sine theta over negative sine theta. So here I get the negative integral of 1 over u squared du. Oh. I'll zoom back out. So that's negative integral of u to the negative 2 du. We go up a power up to -1, divide by the power, gives us another -1, plus a constant. And I've got 1 over u plus c, which is 1 over cosine theta plus c. Which is secant theta plus c. We're gonna do a few more of these on Thursday. But other than that, have a good day. Godspeed.